Let's do 14 because I'm running out of time and it's going to be the longest class ever, that sort of thing, and I'm going to cover some ground. By the way, Bernard, one of the things that could actually shorten the class period is if you did some work.
I'm doing work.
Okay, good. Do you feel like the class is going faster now?
Peter's the one complaining about it.
Bernard started it, and Peter agreed. All right, so I've got a cylinder right here, and what do I know of the cylinder, Bernard?
I tried to
No, its radius.
Radius is 0.08, and its length is what?
1.5.
1.50 meters. Love it. And then I've got over here, I want to find the, it tells me electric field intensity, which is kind of weird, because we keep solving for it. But in this case, we're not solving for it, are we? They just gave it to us, which is nice of them. It's 4.8 times 10 to the third newtons per coulomb, and that's 12 centimeters from the center. Agree with that picture? All right, good. So then it says use appropriate relations. Approximate. Why approximate?
Because it's not an infinitely long one.
It's not an infinitely long one, so we are always kind of, you know, that looks good enough. Let's go with it. Okay? So where do I start this problem, Mr. Bernard?
Write down what this. So you write down the Q enclosed over E naught.
Q enclosed over E naught equals
The integral. The circle. E dot dA.
And we call that closed, just for the record, in case it comes up. It's not likely to, but in case it comes up, I don't want you to go, oh, closed integral, that's completely different.
What is significant about it? Like,
It has to be completely around it.
in calculus, would we see it, or is that
No, you're never going to see it in calculus.
Does that just say like the
This says you have to do the whole entire shape. You're not allowed to just do part of it. This equation is only true if you do the whole all the way around it.
Okay.
If you just do part of a shape, it doesn't work. Equation doesn't work.
Okay.
All right, and so we're going to draw a shape that is exactly, so what shape can I draw that's going to give me exactly everything perpendicular radiated out and the same everywhere I draw it? A cylinder around the cylinder. Good call. So I'm going to draw a cylinder around it. I'm going to choose orange. And that cylinder has to have this radius because that's the one I want, right? It's going to be like this, like this, like this. Now notice how I'm drawing that small. That's why they keep using the word approximate. Approximate, at the middle. Approximate. All right. Good? So let's fill in the blanks. What do you got for me?
Wait, Mr. Sorry, can I ask a question now?
Okay.
Why is it drawn
of the entire thing?
the other?
Flux lines coming out the side.
Why is it drawn upwards?
It has to be completely around the cylinder, right? I have to have all the flux lines.
It's just
So why wouldn't you draw like around?
Because I do not want to get near the ends of this shape. Because this statement is not true at the ends, right? Because the lines are going to curve outwards from there, right? Lines are straight up and down here. And the closer I get to the edge, the more they do this.
So that's just a little segment of it.
I'm just taking a segment of it,
like the circular faces are still on the sides of this.
right? So that when I drew this cylinder, I have circular of those flat sides on the sides, but I'm going to assume no flux lines go through that. That's only true if I'm drawing one in the middle, right? The more closer I get to the edge, the more that's not true. And the worse my approximation becomes. Agreed? All right. So, charge enclosed. You think you mean a charge enclosed?
No, that's what you're solving.
That's what I'm solving for, sort of. So I'm going to go ahead and do that. I'm going to write charge enclosed still, because I don't really understand why that is. This is 8.85 times 10 to the negative 12. This is equal to electric field. Oh, they gave me that. That's nice of them. Times 10 to the third. And then what's my area? What is it? 2 pi r x, which is this length here, right? This arbitrary length x, which is going to be kind of weird. So I'm going to, r is the shape I drew. What's the radius of the shape I drew? 0.12. Good. And so now I'm going to go ahead and start solving for this. And what's weird is I'm going to move the x over here, the charge enclosed, leave it on top. So my charge enclosed over x is equal to, let's do some math, 4.8 exponent 3. I shouldn't say that. That's not even right. Pi times 0.12 times 8.85 exponent negative 12. And I get a lovely 3.20 times 10 to the negative 8th, whatever that is. And so let me make sure everybody's with me. You're with me? Okay, what is it, Karis? Lambda. That's newtons, that's coulombs per meter, right? So that's just going to be lambda. And if that's lambda, they really want to know the charge of the whole entire thing. Well, what's the length of the whole entire thing? 1.5 meters. So what's the charge?
The charge on the shell.
Right. So I found the charge in this little section here. But I didn't even find that. I found my charge being a length through that section through there.
Right.
So if I know the charge being a length through here, how do I figure out what the charge for the whole entire thing would be?
Why would you want that though? It's just
That's what it asked for. What's the whole charge, is it?
It just says the shell. So wouldn't it just be lambda times that x?
Which
A
x?
little bit. The x, the arbitrary x. That you
Yeah, but they want to know that for the whole this whole entire shell, not the shell I drew.
Oh.
The shell, the initial tube, right?
Okay.
So since I want to find for the new tube, and this is going to be coulombs per meter, I just multiply that by 1.50, and I hopefully get the charge of the whole entire thing. About the whole entire thing. And then part B, Mr. Bernard. What is the electric field? What's the electric flux through this? Whoops, that's wrong. What's the electric field at 4 centimeters from the center? 0. Why 0? And no charges enclosed, right? Well done. All right, now to mess with you, I need you to try, start problem number 15. You're going to get stuck unless you're paying a lot of attention in class the other day.
Which one?
The next one, 15. Large planar sheet. I've got my plane like that, agreed? So now I'm going to draw what goes in it. Now here's where things get funny or weird or confusing. Turns out it's not going to matter almost what shape you draw. There's a philosophical reason why I will not draw a rectangle through this. Would be logically a good choice, right? Because you got a plane. So I'm going to put this in here. It's going to hit the surface, and then it's going to come out the back side. How do I draw that? I'm going to draw the back side here. So from a side view, it would look like this. But there's a reason why I would not draw this shape. And what is that reason?
Because the sides.
Because when you have corners, are you really sure there's less flux lines or more flux lines going through there? Aren't you asking for all sorts of trouble? So I want something smoother along that edge. What would be a smoother shape? So we're going to do a cylinder. Cylinder would be a better choice, right? So I'm going to take a cylinder. I'm going to slice it right through this piece of paper. So I'm going to take a cylinder, and basically I am punching it right through the plane. And it comes out the other side, so I can catch rays from both sides. Right? Because the rays would come out both ways. Peter, with me?
Does it have sides? Like that's
Well, if I'm in the middle, does anything travel out those sides?
So it doesn't matter.
So it's not going to have those sides. The only thing you have to worry about is the two end caps. Okay? That make sense, Peter?
Yeah.
So what I'm really going to draw is I'm going to really draw a cylinder punching it because for a philosophical reason. It's only a philosophical reason. It turns out you get the same answer either way. And so where do I start this from, Peter?
Something with halfway in it?
No. No, I always start at the same place.
Then Q over E.
Q enclosed over E naught. I want you to put that little NC down there. Why? Because it's enclosed. The charges outside don't matter. I don't want any part of those things. An integral of E dot dA. And then did I pick a shape that does all the things I'm supposed to do? Is it will the rays be perpendicular to the surface? Yes. Would they be the same everywhere on that surface? Yes. Is it completely enclosed to the surface? Yes. I'm done with all three of those things. I can go ahead and then go like this, EA. And then I'm going to leave you for a little while to finish the problem from there. And then we're going to discuss a rather large epiphany that is frightening.
Q equals halfway.
They give me charge per unit area, right? So they give me charge per unit area. The only way to do charge is charge times the area enclosed, right? So look at my picture. What's the shape of the area enclosed? It's a circle, so I'm going to go pi r squared. Now I'm going to be very aware of the fact that I picked the r. It better cancel out. Right? The radius of the circle is the radius of the circle I drew. Yeah, that shouldn't, no. No. Okay? So E naught equals, what's the electric field? That's what I'm looking for. What's the area of the shape I drew? Whoop.
Why is that on top? I have a question.
Hat boy?
That's hat boy.
That's right. Charge per unit area times the area given its charges in that surface, right?
Okay.
That good enough? Good with me?
Yeah.
Okay. All right. Electric field is what I'm looking for. What's the area of the shape I drew, Peter?
Pi r squared.
But I got two of them, don't I? One up, one on top, one on the bottom.
So
2 pi r squareds. Now notice something extraordinarily interesting. What happens to the pi r squareds?
They cancel.
Which they have to because I wanted the radius not to matter. So I bring the 2 over there. I go hat boy over 2 E naught equals the electric field. I'm going to circle that temporarily. There's something weird going on here. Mr. Bibele, what's weird about this?
The shape doesn't matter.
Well, the shape doesn't matter because I picked squares. Squares wouldn't have mattered. Whatever the shape is wouldn't matter. So it's a philosophical point of view. We said it doesn't matter. What's weirder than that?
You could just make that.
You could make that a formula if you knew what it was. I got weirder than that. What doesn't matter that you feel like fundamentally should?
The size of the cylinder. The charge of the sheet.
Charge of the sheet matters right there.
The shape.
The E naught permittivity of space matters, yes.
You
could make this.
The 2 is down there, that's interesting. What matters, sir?
The space the circle is from the sheet.
How far it is from the sheet. The electric field doesn't matter how far it is from the sheet. There's no place for the distance between you and the sheet. It doesn't matter. Why doesn't it matter? Because the sheet is very large. And you are very close to it. The farther you get back, the more things pushing you this way, right? The closer you are, less things pushing you. They're pushing you laterally and canceling out. So as long as you're close to the sheet, how far you are doesn't matter. And that brings up into that game that we just talked about a second ago where we had 2 plates. What's true about the electric field between the 2 plates?
They're equal.
It's equal everywhere between the 2 plates. Why? Because it doesn't matter how far you are from those plates. They're both doing the same thing. As long as you're not near the what? Edges where it starts to do something weirder. Yeah?
This is silly.
What?
Silly class.
Is there a charge per unit volume?
Yes.
All right.
It's on the front page. Hope you wrote it down at the time.
You ready?
Yes. You lose things, but that's not what we're talking about. All right. If I have a solid conducting sphere, I've got a negative charge here. What do they do, Brandon?
They go away from each other.
And since they're conducting, they can, right? And so they're going to run to the opposite sides, right? If I put a third one, I drop a third one in there, what's going to happen?
Sad.
I have one here, one here, one here. If I put a fourth one, what's going to happen? They're going to keep moving around to get away from each other. The farthest distance they can is along the what? The edge. So the charges are going to move so they get to the edge and are symmetric. Isn't that nice?
No integral.
So we don't have to do the integral or do anything like that. All the charge in a conducting sphere or conducting anything will run to the edge as far as they can get away from each other. As long as it's a nice shape like a sphere, we know it's going to be symmetric around the outside.
Wait, so it's gonna just be the same thing as a shell?
It's going to be like a shell. A conducting sphere makes it into a shell.
Dang it. I was
Okay,
doing-
which means the next step would be a non-conducting sphere, and then we're going to have fun to play with.
I was doing.
We'll get there.
So for 17, it's just the same thing as a shell?
17.
Or do you use the volume?
A solid sphere, the total charge, uniformly distributed. Oh, that one, no. That one's got charge inside, outside, all over the place,
Well,
uniformly.
this one has charge inside